right, the first question asked for was 6. 6 asked to find the sum starting at 1, going to infinity of n sine of 1 over n. So we learned various tests that we could try to apply to this. I said my favorite one is the ratio test. I would not apply the ratio test on this one, however, because there's no exponents of n's and there's no factorials. And that's where the ratio test is typically the most helpful. So the ratio test, as much as I love it, probably not a great go-to on this one. We learned our comparison test, which we can use to kind of squish down a function. When I have sine in there, sometimes I consider that one because we can block sine off and say the biggest it can be is 1. But since this isn't just a sine, it's a sine of 1 over n, that makes things a little bit trickier to block it off. So another test that we learned was the nth term test. And the nth term test says we need to make sure our terms are getting smaller. So as our limit, as n goes to infinity of our terms needs to be 0. If this is not 0, then our terms are not becoming 0, and we are always then adding something of value. Okay? If our terms are becoming 0, then in the end we're really adding nothing of value, and so we have a chance to converge. It doesn't mean we do, but we would have a chance to converge. So if I plug in infinity right now, 1 over infinity is 0. Sine of 0 is 0, and so I would have infinity times 0, which we actually learned is indeterminate. So I'm going to rewrite this as sine of 1 over n over 1 over n, which is exactly the same thing. I haven't changed the problem, but algebraically, instead of multiplying by an n, I'm going to divide by the reciprocal, 1 over n. It's exactly the same thing, but now it is something that will work for L'Hopital's. So when we do L'Hopital's, we take the derivative of the top, which would be cosine of 1 over n, times the derivative of 1 over n, which is negative n to the negative 2. We need a chain rule on that. And on the bottom then, the derivative of 1 over n is negative n to the negative 2, which goes away. So now, as n goes to infinity, 1 over infinity is 0, and cosine of 0 is 1. And what that means is our terms are not becoming 0, our terms are becoming 1. And so then 1 plus 1 plus 1 plus 1 forever is not going to add up to anything other than infinity. So this is a divergent series. So we would say divergent by nth term test.
I thought calculators couldn't calculate something as indeterminate. Because on mine, when I plugged in, I plugged in like a trillion or something.
Oh, but that's not infinity. You didn't plug in infinity. You plugged in huge.
Right. I plugged in huge, and it gave me 1.
And it gives you 1.
So is that pretty much a good thing?
On a calculator part, sure. Yeah, on a calculator part, that's a good way to quickly try to test an nth term, is to do something really large. But what you plugged in wasn't indeterminate, because you plugged in a number. You didn't plug in infinity. So if we truly think about infinity, then it is indeterminate.
I put absolute value sticks around sine, and then did the limit as n goes to infinity, and then I got infinity. So it diverges. So is that maybe another way to do that? Or?
Yeah. The next problem asked for was 15. 15. We're asked to determine whether or not this series converges. I see factorials, and factorials, my go-to is the ratio test.
I feel like this is, after this assignment, the ratio test instantly became my go-to.
It's my go-to. I love
I was
it.
just like, hey, I just do this.
Yep.
It works. It works.
It works for a lot of stuff. It doesn't always work, but it works a lot.
Yeah.
So the ratio test says plug in n plus 1. So I'm going to have n plus 1 factorial over 2 n plus 1 plus 1 factorial. We're going to need a little cleaning there. And then divide by the original series or the original term, but I'm just going to multiply by the reciprocal. I need to do a little cleaning on the bottom of this thing. If I distribute 2, I'm going to get 2n plus 2 plus another 1 is going to give me 2n plus 3.
There's 2n plus 1 and the parentheses are plus 1.
And then we can start trying to cancel some factorials out here. So n plus 1 factorial means n plus 1 times n and so forth. N factorial means n and so forth. So that cancels out everything except for the first n plus 1. Now 2n plus 3 means 2n plus 3 times 2n plus 2 times 2n plus 1, etc. So I can cancel the 2n plus 1, etc., but I'm left with the 2n plus 3 and the 2n plus 2.
Well, wouldn't it go 2n plus 3 and 2n plus 4?
What is that?
We count down.
Squared
For a
plus
factorial, we count down.
5n plus 6.
So it's only constants that are affected by the factorial.
Yeah, what if it was just 2n factorial?
Then it'd be 2n minus 1. Because when we do a factorial, we're taking a number and multiplying it by 1 less. 1 less just means subtract 1. So we're just subtracting 1 from it each time. Until we would get down to 1, and then we stop multiplying, because otherwise if we multiply by 0, factorials become really boring.
So you want to multiply by like just 2n at the end of it?
The last thing we would multiply by would be that. So then I'm left with, on the top, an n plus 1, and on the bottom, the 2n plus 3, and the 2n plus 2.
Could you factor the 2 out of the 2n plus 2?
You could. So there's a couple of strategies for how to simplify this thing now, because if I plug in infinity at this point, I have infinity over infinity times infinity. So that's a whole lot of indeterminate going on. So there's 2 main strategies you could use. So one is, like Daniel said, we could factor out the 2, and then we would have an n plus 1 that would cancel. Okay. The other one is to just FOIL out the bottom, or notice that even without foiling, it's going to end up being a quadratic, right? So it's going to be a 2n squared plus stuff. So then when we apply a L'Hopital's, we're going to get 1 over 4n, which is going to be 0. What does that mean? It means convergent. Okay. Ratio test says we have convergence when the limit that we get is less than 1. 0 is less than 1, so this is convergent. And we would say convergent by ratio test. Yes.
I got a text from Peter asking if you could record the lesson.
It is.
Oh, Peter's sick.
Conference, I think.
Celebrating dates, Victor.
Peter.
Yeah.
I'll pretend like, yeah, I didn't hear that. Yeah.
It wasn't
18.
an hour. A bird flew in and gave him a message.
18 says find 2 convergent series. But we want this to diverge. Okay, so we want 2 individual series that converge, but we want their quotient to diverge. One of the easiest types of series to think about convergence and divergence for is a geometric series. Okay. So if I let a sub n be 1/2 to the n, that would converge, right? A half times a half times a half times a half, they're going to get smaller. It's going to converge, right? That's geometric. If I let b sub n be 1/3 to the n, that's going to converge, right? A third times a third times a third, they're getting smaller. It's going to converge for our geometric. So then a half to the n over a third to the n is a half over a third all to the n. And how do I do a half over a third?
It's just bigger than 1.
Multiply by the reciprocal.
Right, 1/2 times 3 over 1, which is 3 over 2 to the n, which is divergent because our ratio is now bigger than 1.
If I just had 1 over 2n.
That's the same thing. Not 2 to the n, not
If I
2
just
times
had
n.
2 times n.
That is divergent.
1 over
That's
2
not
times n.
convergent. Yes. We will talk a lot more about that very special series in section 5, but 1 over 2 times n is divergent.
Is 1 over n cubed convergent?
Where did you get
I believe so, but we would have to do a test on it.
Okay.
I'm not positive. Oh, yeah, I'd have to do a test on that.
You just put number 1/3 and half.
Yeah, I just kind of picked them. So,
Can you just pick between
Any numbers as long as they're 0.
um,
It's bigger than the other.
see the next one asks for,
this is 3.
yeah,
For half and 1/3, can you just pick out any number between 0 and 1?
yep, we just want to pick some fraction because a fraction smaller than 1 is what's going to give us the convergence. And then I wanted to pick it so that my a was bigger than the b, so that when I would divide them, I'd get something bigger than 1.
What if it was 1 over 3n?
Still divergent. 1 over 3 times n is divergent. We will talk a lot more about that in section 5.
Why?
We'll talk about it in section 5. 39. 39 asks for
39.
39 asked for the interval of convergence. For an interval of convergence, so far, all you know to do is either a ratio test or geometric. Okay? The nth term test doesn't tell us when it converges or diverges, just if converge or diverge. It can't give restrictions. Our comparison test also just tells us a yes, no. Well, yes, it doesn't actually tell us if it converges. It tells us if it diverges or question mark. But it doesn't tell us an interval. The only tests that we have done that can give us an interval are ratio or geometric. I don't see lots of factorials here. I do see a power of n, but I don't see factorials. This is actually a geometric series. If we would start by plugging in values of n, if I started plugging in 0, I'd get 1. Then if I plug in a 1 for n, I get this. If I plug in a 2 for n, I get this squared, etc. So what am I multiplying by each time?
That, yeah.
So this needs to be between -1 and 1 for convergence in a geometric. So I multiply by -3. Just by +3, sorry. I add 1. And then I cheat and take a square root. So I get negative the square root of 2 to 2.
Yeah, here's the problem.
Yeah.
That's not what the answer has.
No?
It says just -2.
But I figured out why. Oh, no, it says that between -2 and 2.
Yeah.
That's because if you were to square -2, you get a +2. Then you get 2 minus 1 over 2.
Huh?
I don't know. Hold on, I had it in my head.
Yeah,
All right, so what we're going to do
That's why I asked this.
is at this point, I'm going to add my 1, and I get a -2 to 4.
I think it's because
I use the absolute.
I can't just do the absolute value because this isn't a symmetrical interval. So like if I think about this on a number line, it's not symmetrical about 0 right now. So I can't just say the absolute value of x is less than 4 because that should go from -4 to 4. So what I would have to do is kind of like recenter this. So this has a length of 6, so its center is really like here. This is a tricky problem. So I can rewrite as if I'm shifting over to a positive one, I would want to do x minus 1 squared. And then I could do an absolute value of that. And then I would use a 3.
Yeah, that's what I would think.
Straight up.
Which I don't think helps.
But then that doesn't help
I think
us get the answer on the
I think I might
sheet.
know what the people were doing.
Just straight up.
Is that
I figured out what they did.
but you're trying to figure out.
I think they just
like-
added wrong.
Just straight up.
What they did makes sense.
Like you want the area to be you basically want x to be in between -1 and 1. So what they did is that they try to figure out what x has to equal in order to make sure that it's not 1 over 1. And so in this case it's negative x and 2. -2 and 2, and if you square that and then subtract when you get 3 over 3, which is 1 to the n power.
I'm just uncomfortable when the algebra doesn't confirm that.
Yeah.
I use the x
But if you
squared
plug
minus
in
1 divided
-2,
by 3, I make
works.
that absolute,
Yeah.
and then it's like smaller than 1. And then you will get x squared minus
So-
1 is smaller than 3.
The problem with that is I can multiply by the 3 and that's fine. But I can't add 1.
This is what they did. They just added the 1.
Yeah.
Yeah, but you can't. It doesn't always work.
Just add 1.
In
It'll
this case,
always
it
work.
In this
So-
case, it works.
Yeah, I'm a little uncomfortable with that. So,
The book didn't go or did it right. But
The
it
algebra
uns-
makes no sense.
the algebra doesn't really confirm it though. There's some algebraic sketchiness that happens there.
the
So-
book did it
Question the
right
sources too.
So which one do we accept?
51 I'm not going to talk about. 51 is telescoping, but with arc tangent. Can do it.
Okay,
It's
no.
just
Is
man,
telescoping
it's
just-
not.
Instead.
Is it just me or is telescoping really easy?
Telescoping, you just have to find out what the first term is,
Yeah. Is that
and
all
then
you have to
everything
do
else
every
will
time?
disappear.
Will the AP
Yeah.
test be like
So-
questions on See, all you do is
Literally
plug
plug in 1.
in. Wow, sorry.
So,
Or is it 0?
I mean,
Depending- whatever's on the
for telescoping,
1.
we would, well, that's an N right now, but since it tells us it's telescoping,
Yeah, it says 1. Yeah.
this is not that bad of a problem. If it didn't tell us telescoping, this would be a horrendous problem. Okay? But since it tells us it's telescoping, and a telescoping, the first term is what's going to matter, and everything after that is going to collapse on itself. So we really just need to plug a 1 into this and see what we get. And arctangent of 1 is pi force. And arctangent of 2 is not pretty.
Arctangent of 2. But if you keep going, the arctangent of 2 will flatten itself, and it ends up at just pi fourths. Because next it'll be.
Oh yeah, because the next term will cancel that arctangent of 2.
Yeah.
So
Wait, explain to me.
Oh,
John.
okay.
because then when I plug in a 2 for my next term, I'm going to have an arctangent of 2 minus an arctangent, that doesn't look like tangent, but pretend like it does, of 3. And so then they're all going to go, and I'm just going to get left with that first one. Pi force.
Wow, that's
Since it tells us it's telescoping, it's not a horrible problem. If it didn't tell us telescoping, this problem would be a little overwhelming.
I would cry. And
Says what we're going to do is let our series become an integral, because an integral is really just a fancy adder, right? We talked about that when we're finding the area under the curve, we could create all those rectangles, and then the integral adds them up, right? So an integral really just adds up a lot of stuff. So what we can do is take our series, which adds up a lot of stuff, and turn it into an integral, which adds up a lot of stuff. And if that integral converges, then the series will converge. If the integral diverges, the series will diverge. This doesn't necessarily tell us what the series converges to. Okay, so when the integral converges, that means we get an actual answer. So we integrate and we get an answer of 4. That means the integral converges, has a value. That does not mean the series converges to 4. It means the series converges. We don't know what it converges to. Okay, but they both do the same thing. So they either both converge or they both diverge. So our first example wants to look at the series of 1 over n times the square root of n.
Yes.
We are going to do our integral test on this. Integrating from 1 to infinity, because that's where the series is going from. It's from 1 to infinity. When we change it to an integral, we typically change it to x's. It doesn't really matter. It's just a notational thing. It's not a big deal. Just typically when we're integrating, we're talking about a function, so we use x because x is a function letter. We want to rewrite this to be able to integrate this more easily. We can't integrate it the way that it looks now.
X to the negative one.
So this is x and x to the 1/2, which is x to the 3/2. But on the bottom, that's going to become an x to the negative 3/2.
Is it really not a trigonometry sort of thing?
It is not. Now, this is an improper integral, so we really need to write limit as b goes to infinity of 1 to b.
Nope, that should really only matter if we're doing a free response, right?
Free response, do this. Multiple choice, don't waste your time. But really, technically, we do need this because we can't actually evaluate the integral out to infinity. When we evaluate that integral, what do we get?
Negative.
Negative 1/2
Yeah. No, negative.
times negative 2 over 3.
What's the exponent?
The
Negative
exponent
1/2.
is
One
negative 1/2.
So what's the coefficient?
2.
2.
Negative 2.
Yeah, that one.
Okay, so we raise the power by 1, so the power becomes negative 1/2. We divide by that power, so dividing gives us negative 2. We're taking this thing from 1 to b. So then I'm going to plug in b minus plug in 1. As b goes to infinity, square root of infinity is infinity, negative 2 over infinity is 0 plus 2. So this integral converges. That means the series converges. It does not mean the series converges to 2. Okay? It means the series converges, but we don't know what to.
Can we find 2?
We cannot.
Where can I? We cannot.
We cannot find out what it converges to.
Wait.
We can just know that it converges.
What were the values that if it's over 1, we get an
If you get a number answer.
okay.
If you get infinite, then it diverges. If you get an answer, then it converges.
Yes. Oh, is the only way to tell what something converges to? Is it that starting number over 1 minus
Yeah.
that? And
So at this point, the only thing you can do if you need to know what it actually converges to is it has to be geometric. So you can do a over 1 minus r, or it has to be one of our Maclaurin series, like an e to the x series as an e to the 1. Then we would know it converges to e. But unless we can line it up with one of those Maclaurin series, then we can't know. The next part of the note talk about this very special series that John was asking about when we were going over the homework, which is the harmonic series and the P series. So we're going to start this with an exploration to look at this harmonic series. The first part of the exploration says, use the integral test to prove that actually, I don't think we are going to look at this whole thing because we actually already did this in the last chapter, but we'll still outline it. Prove that this converges if P is bigger than 1. So in the last chapter, we actually did problems like this, but we were talking about integrals. So we were going from 1 to infinity, 1 over x to some power, and we said we actually went through the integration in an example there, and we said that when that power is bigger than 1, we have convergence. When the power is smaller than 1 or equal to 1, we have divergence. Okay. So the question John was asking in the homework was he was trying to use the series 1 over 2n. That is like 1/2 of 1 over n, which has a power of 1, which is divergent, and half of divergent is still divergent. Okay. This series of 1 over a first power, so whether we're talking about x or whether we're talking about n, this series of just 1 over with the power of 1 is called our harmonic series. The reason why it's called harmonic, it kind of outlines in the book as being, if we start finding out terms, if our series is 1 over n, we've got 1 over 1, 1 over 2, 1 over 3, 1 over 4. If we start to take these in terms of like lengths of vibrating strings, then we get, musical notes in harmony, and that's why this is called a harmonic series. It is important to know that the series with the power of 1, so 1 over n, is called the harmonic, and it is really important to know that it is divergent.
Yeah, we could use this in the last equation.
We could have used this in the last problem, because in the last problem we were evaluating the series from 1 to infinity of 1 over n to the 3/2. Power's bigger than 1, convergent. Okay, and it's that easy on a free response question too. You don't have to go through the whole integral test.
So
you could just say convergent by P series.
By P series? Harmonic
Harmonic is if it equals 1, and then P series is any other power.
If you multiply the harmonic by 1 over 100, would it still work?
Harmonic would still be divergent. Harmonic is divergent. 1/100th of infinity is still infinity.
What? No. But what if you were going 1/100th plus 2/100ths, or 1/100th plus 1 over 200 plus 1 over 300? Would that still do it?
That's still just the harmonic with 100. So. Yep.
What if it was 100 over?
That doesn't matter either. So you can change the top, because if it was 100 over n, I can say that is 100 times divergent, which is even worse divergent.
Or better, depending on how you
Right. Depending on whether you want to converge or diverge.
I like Divergent.
There's
a movie coming out called Divergent.
There is. I'm excited about it. It came out last night.
It's literally just about math.
You mean it's not about math? Maybe I'm not excited about it. Hold on. I was excited. No. I have actually read the books, and they are good, and I'm excited.
You go in there, you got your popcorn pop, you're like, alright, here we go.
Alright, I'm ready for some integrals. Bring it on, right?
Your calc book.
He's like, wait a second.
Comparison test. Comparison test relates to an idea that we actually studied again in chapter 8, where what we're going to do is compare two functions. So we talked about one comparison test in the last section, and that was the comparison test where we squeezed down one function to make a smaller one converge. Our other comparison test is where we want to find two functions that behave the same, And then we can say if one of them converges, the other one does as well. And we talked about this in chapter 8 when we talked about the idea of growth rates of functions. And we said if they both grow, or really in this case we're thinking of shrink, because we want our series to get smaller. If they shrink at the same rate, then they're both going to have to converge or they're both going to have to diverge. So what we're going to do is find another function that we believe should behave the same for really huge values. And when we talk about really huge values, we're talking about a limit as n goes to infinity. And we're going to take the fraction of these two functions. If we get some number other than 0 or infinity, they both converge. If we get 0
Or diverge.
or diverge, yeah. They both do the same thing. Yeah. If we get 0 and the bottom one is convergent, then the top one is convergent. If we get infinity and the bottom one is divergent, then the top one is divergent. If we get 0, when we talked about growth rates of functions, what did that mean? Which of these is growing faster?
The bottom.
The bottom, right? Because if you get 0, that's because we had something over infinity. So if the bottom's growing faster and converges, then the other one must still too. And for the third one, if we get infinity, then that means that the top one must have been growing faster. So let's look at some examples of how we can pick these things to compare and then evaluate our limits. Example 3 has parts A, B, C, D, so there's kind of a lot of examples in here. So the first example, and if you're looking in your book, I'm going to ask that you don't shout out the answers and cheat, because I want us to kind of practice coming up with series here. So the book tells us the series, but I want us to try to come up with it. So I want us to come up with our general rule here as some practice. So if this first term is 0, 1, 2, 3.
Is that supposed to be 6 over 16?
It should be 7 over 16.
Good, then the pattern actually makes
Okay.
sense.
I was like, what?
All right, so we're starting this thing at 1, and we're going forever. So what would I do at the top? Okay, so it's an even odd. How do we handle even odd?
2n plus 3.
2n, and then we need to adjust to our start. I'm starting us, I'm going to start us at 1 because that's what the book starts us at. It doesn't really matter, but just to be consistent there. Okay, so if I started at 1, then what do I need to add to adjust? Plus 1. The bottom, what do you notice about those bottom numbers?
They're being added by...
They are perfect squares. And they are the perfect square of 1 more than where they are in line.
Okay. That's what you said.
All right, so that is the series that we want to be able to tell if this thing converges or diverges. So what we want to do is find another function that we can say, for huge numbers, this is pretty much the same thing, right? For huge numbers, adding 1,
doesn't matter.
Not such a big deal, right? For huge numbers, adding 1 on the bottom, also not such a big deal.
That's a much easier one.
When we reduce this even more, so this is approximately the same, now this one is exactly the same. If I reduce that, I get 2 over n.
Oh, beautiful.
Now, we need to actually show that adding 1 doesn't matter. And the way that we show that is by taking a limit as n goes to infinity of one of these things over the other one. So I'm going to multiply.
Hey, this is sort of like the ratio test.
This is the ratio.
And
No.
on the top then I get 2n squared plus n. On the bottom, if I distributed all this out, squaring this out, I would have an n squared but then times a 2, so 2n squared. Then I'd have a 2n, but I'm multiplying by, so I get 4n plus 2. Okay, I went through all the foiling there quickly in one step.
For us.
But if I FOIL that all out, this is what I end up with. If I plug in infinity, I get infinity over infinity. But I can do a L'Hopital's, and what's going to happen in the end with L'Hopital's?
It's gonna be.
We're gonna get 1.
We're just going to end up getting 1
Yeah,
from those
four.
coefficients there. So we got a constant, which means they do the same thing. So then the question is, what does this one do?
Diverge.
Why?
Please excuse this interruption. Ms. Dreyer, please come to the high school office.
Right? That
If
thing is
I-
harmonic.
If I said P series there, would I be okay?
Yeah.
So to be safe, just say P series.
I don't know. It's important to know what the harmonic is. So that one's harmonic and diverges. Since they do the same thing, the original one diverges.
So the harmonic is the P series
With power 1.
power 1. On that. Well, for both of them.
What does the guitar picture have to do with it?
Harmonic.
There's a great pattern here somewhere.
There is.
Uh,
Does it have anything to do with mathematics though?
Yeah, that's why it's called harmonic. It's like where you place your fingers. That's why the frets are where they are. All right, so we want to come up with our series here.
what'd you say down there?
1 over.
All right, so we got 1 over. Good with that. All right, now these numbers down here.
It's 2, 4, 8 gaps, which is helpful somehow. And 2 to the n. Is it 2 to the n?
No, it's not.
Somewhere helpful in here.
2 to the n is definitely helpful in here. This is a really hard one. I wouldn't expect you to actually have to recognize
Don't
this.
give it to
But what
Minus 1.
what you
2
would
the
kind of
n
need to
minus
notice,
1.
you have to have like such a strong sense of numbers that you notice that these are 1 smaller than powers of 2, because powers of 2 are 1, 2, 4, 8, 16. Right? So these are 1 smaller than powers of 2. So this is 2 to the n minus 1 on the bottom.
How are we supposed to get
I
this?
thought it was n squared.
That's not necessarily something that I would expect most students to be able to recognize. That one's pretty brutal. You have to be very comfortable with your powers of 2 to be able to see that one. All right, so now, if I'm trying to find something to compare this to, subtracting 1 does not seem like such a big deal. Right?
Yeah.
So, we need to prove it's not such a big deal.
Is this the ratio test that we're doing? Or is it?
No, it's just similar.
It feels like it's like almost.
No, think about it.
Because we're not plugging in n
That's
plus
true.
1,
True.
which
Yeah.
is what the ratio
Well, I
test
think
is.
about
What
in this
is
case.
this then?
This is comparison test.
Daniel,
Okay.
it worked in the last case, but when you flip over this time, the
If
right
there's
side will
not
be
a
bigger.
number that doesn't matter to me,
Because it's 2n minus
Then a
1.
comparison test wouldn't be the best way to go.
Yeah.
then what would you use instead?
A different test. It would depend on what the problem was.
Actually, it's not bigger, but it's
AP tab.
Alright, so I end up with to the n over to the n minus 1. Here we get infinity over infinity.
And you can't really fix that.
And you can't really fix it because when you start taking derivatives of this thing, well, we can fix it. When we take a derivative of it, you're gonna get ln of 2, 2 to the n. On the bottom, you're gonna get ln of 2, 2 to the n. So we get 1. That means they do the same thing.
Ooh, how did you just cross those two off?
Because they're the same.
Oh,
both.
You crossed the
The
element.
whole thing, gone. This gone.
Okay, I just thought you crossed off
No,
the
the
element
whole
2
fraction
with the
gone.
2n.
No.
And I'm like, wait, how did this just happen?
Whole fraction gone.
Also,
So
give
now
me-
they do the same thing. So the question is, what do they do? So this is not a P series because a P series,
It has to be n to
we
the
need we need to have like an n to a power, not a power to an n. So
Divergent by harmonic series?
it's not a P series. It's not harmonic.
Divergent because we want it to be.
What does raising to a power do? What's that mean when I raise something to a power? I'm multiplying it by itself. What kind of series is that?
Geometric.
Geometric. This is 1/2 to the n.
Which is
Convergent or divergent?
Divergent. No, and convergent.
That is convergent.
To 1/2 the n.
Okay, that is convergent because the ratio is smaller than 1, which means both are convergent.
So exponentials of fractions are usually convergent and
It's a fraction smaller than 1.
okay.
Geometric.
Geometric is
Yeah.
Down on the bottom, you took the derivative of it. How did you get those things?
The derivative of a to the n is a to the n ln of a.
Okay. Then where the negative one go?
I took a derivative.
Sacrificed so
For the greater good.
I'm too afraid to take it off.
Yeah, but
We'll pick up with the middle of that example
square minus 1.
on Monday.
It's ln of
So we didn't finish lesson 5. That means no lesson 5 homework.
Yes.
Journal. Don't forget about your journal, and it is a series journal.
I dropped down a small
We are studying for lunch.
Yes. But actually, like, I picked it up.
Woo!
Shattered. Except for okay, but English.
The derivative of a to the n is a to the n ln of a. So what we call it.
I picked it up in the stone.
Yeah.
What kind of parallel universe is we entered? Someone breaking us. Someone breaking
This is not, you can't do that. So we need to integrate this with a u substitution.
So last night's the notes from our stuff. So I went on YouTube and looked up Patrick J. And when he was finding the interval of convergence, he checked the endpoints.
We're going to talk about that in this section. You don't have to do that for geometric,
Okay.
but when you do a ratio test, you do. And we'll talk about that in this section.
I don't even think the first one was they were over like tech testing it, and they had where they were just go
ahead. Yeah, he asked. He asked.
Hey John.